Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on November 25th, 2025, about 3 days ago. It shows that a large physics foundation model, trained on a huge collection of simulation data, develops simple internal directions that you can tweak to literally turn physical behaviors on or off in its predicted simulations, like adding or removing vortices or changing diffusion. The paper is titled Physics Steering: Causal Control of Cross-Domain Concepts in a Physics Foundation Model. And as we will see later, the implications for scientific discovery and model control are pretty remarkable. Alright, Figure 1 lays out the whole steering pipeline, which turns raw simulations into a concept direction and then feeds that direction back into the model. The left panels show laminar and vortex flow movies going through the physics model to produce internal activations. These activations split into two groups, with and without the feature, and their mean difference defines the delta vector. That single direction is then added at inference time, so the right panel show new simulations where the targeted physical feature is strengthened or suppressed. Well, Figure 2 shows what happens when the model receives negative vortex steering on a shear flow that initially contains strong vortices. The three rows compare the true flow, the steered prediction, and the resulting error. As alpha becomes more negative from left to right, the swirling vortex pairs flatten, and the flow becomes increasingly laminar, so the bottom row gradually loses those tight spiral cores and shows smoother, more parallel structures. So while Figure 2 showed vortices being dialed down, Figure 3 demonstrates the opposite effect, as the model actively creates vortices in an initially laminar shear flow. The three rows again display true field, steered prediction, and error. As alpha increases from 0 to about 0.4, the middle row gradually develops clear swirling lobes. The bottom error row reveals that these new vortices emerge as structured deviations rather than random noise, which supports the idea that a single learned direction genuinely controls vortex formation. Alright, Figure 4 broadens the story by showing that the model also learns controllable directions for diffusion and for effective speed. The left column illustrates diffusion steering. Increasing the diffusion direction smooths and blurs the tracer interface, while decreasing it sharpens the vortical cores and boundaries. The right column presents speed steering, where positive injection advances the development of the shear layer, and negative injection holds the flow back in an earlier, less evolved state. So, while Figure 4 focused on shear flow, Figure 6 shows how the same learned directions transfer to very different systems. The left column displays Euler density fields with vortex steering, where increased steering strengthens swirling structures and decreased steering smooths them out. The middle column applies the speed direction, so the vertical shock front moves noticeably faster with increased steering and slower with decreased steering. The right column is the surprise. Positive vortex steering reshapes Gray-Scott chemical gliders into spiral-like patterns, suggesting a very abstract notion of rotation. So, while Figure 6 highlighted cross-domain transfers, Figure 5 zooms in on Rayleigh-Benard convection and shows how the vortex direction reshapes buoyancy and pressure fields. The top panels, which average over space, move from smoother, less structured flow with decreased steering to strongly modeled rotational structure with increased steering. The bottom panels, which keep full spatial detail, display even richer plumes and rolling cells as steering increases. The comparison indicates that the single vortex direction really does inject or suppress convection rolls, not just noise. Alright, the previous figure highlighted how steering reshapes convection patterns, and Table 1 now grounds those visuals in concrete simulation data files. The left column lists which figure and panel each experiment came from, so every steering result ties back to a specific run. The right column shows the corresponding file names, which encode parameters like Reynolds number, Schmidt number, and physical setup. This mapping matters because it lets researchers reproduce or extend the experiments using exactly the same underlying simulations. So the big takeaway is that a single learned direction in a physics foundation model can reliably turn physical phenomena on or off, from vortices to diffusion to effective speed. More strikingly, those directions transfer across very different systems, hinting at genuinely abstract physical concepts. That is it for this episode of AI Research Roundup. I am Alex. Thanks for listening.